All right, let's get into it. Today, we're going to put on our detective hats and investigate one of the sneakiest, most destructive problems you'll find in any rotating machine: misalignment. You know, it's one of those tiny errors in setup that can cause an absolute catastrophe down the line. So, let's dive in and crack this case.
So picture this. You've got a critical piece of equipment, and it's running. But something's just not right. There's a weird vibration, maybe a little extra noise. You can just feel that it's straining. Well, that's our crime scene, a shaky situation that tells us there's a hidden threat lurking inside. So, what is the silent killer? I mean, it's not always the most obvious bad guy. It's a fundamental flaw right there in the connection between two components, and it's behind a massive number of machine breakdowns. The culprit? You guessed it, misalignment.
And the stakes here are incredibly high. We're talking about a tiny, tiny error in alignment creating these immense stresses. This is what chews up bearings, wears out couplings, and can even shear bolts clean off. The driver, the motor, it has to work way harder, which means it's sucking up more power and overheating, until, bam, the whole machine just grinds to an unplanned and always expensive halt.
Okay, so how do we catch this thing before it causes a total disaster? Well, we have to crack the vibration code, and our number one forensic tool for that is vibration analysis. It's kind of like we're listening to the machine's heartbeat. By analyzing its vibrations, we can diagnose what's wrong, almost like a doctor reading an EKG. Now, right away, our investigation hits a bit of a snag. See, the symptoms of misalignment often look a lot like our other prime suspect, unbalance. Unbalance is pretty simple. It's just a heavy spot on a rotor. Think of a car tire that needs those little weights. Misalignment, though, is about the positioning between two different parts, say a motor and a pump. They can look really similar on the surface. So how in the world do we tell them apart?
The tie-breaking clue, the thing that cracks the case wide open, is something called phase analysis. And really, the idea here is pretty simple. Phase is just a measurement of timing. It asks, are two different points on this machine vibrating in the same direction at the same time? Or are they moving in opposite directions? This one measurement gives us all the evidence we need to tell our suspects apart. So now that we have our special forensic tool, we can start to build a profile for the usual suspects. See, misalignment really comes in two main flavors, and each one has its own distinct signature, its own criminal profile that we can spot. First up in the lineup, we have angular misalignment. This is when the center lines of two shafts aren't perfectly parallel, they actually meet at an angle. Its vibration signature is a strong shake back and forth in the axial direction at the machine's running speed, which we call 1x RPM. But here's the smoking gun, the absolute giveaway, the phase. The two sides of the coupling are vibrating 180 degrees out of phase. That means as one side pushes forward, the other pulls back. It's a dead giveaway. Our second suspect is offset misalignment, sometimes called parallel misalignment. In this case, the shafts are parallel, but they're not in the same line. One is shifted up or down or side to side. Its signature is a strong radial vibration. That's the up and down or side-to-side movement at both 1 and 2 times the running speed. And just like its partner in crime, it gives itself away with that classic 180-degree out-of-phase reading across the coupling, but this time you measure it radially. Of course, in the real world, things are rarely so clean-cut. Most of the time, what we actually find is a combination of both angular and offset misalignment happening at the same time. And that's what makes this detective work a real skill. You have to carefully measure and untangle all those combined symptoms to find the true root cause. But hold on, our investigation isn't over yet, because sometimes the problem isn't at the main coupling at all. Misalignment can be a real master of disguise, hiding in other parts of the machine where you might not even think to look. Let's unmask a few of these hidden culprits. Okay, let's talk about bearing misalignment. This happens when the shaft isn't sitting perfectly straight inside its own bearing. A really common cause for this is something called a soft foot. That's where one of the machine's feet isn't sitting flat on the base, so when you bolt it down, the whole frame gets twisted, forcing the bearing into a misaligned position. And here's where things get really sneaky. Bearing misalignment causes strong axial vibration. But what's so devious is that balancing the rotor can sometimes make the vibration go down. So you're tricked into thinking you solved the problem, but the root cause is still there. The real clue is a very unique phase pattern. If you take readings around the bearing housing, top, bottom, left, and right, they'll be 90 degrees apart from each other. That's the telltale sign. Another classic hideout for misalignment is in any belt-driven system. Pulley misalignment is when the two pulleys aren't in the same plane. You can think of it just like the angular and offset misalignment we saw in shafts, but for pulleys. And this is a super common problem that puts a ton of stress on the belts, the bearings, the whole machine. The big giveaway for misaligned pulleys is high axial vibration, that back and forth movement, at the running speed of one of the pulleys. And what's really key is that this axial vibration is way stronger than any radial vibration. That single fact helps us know it's not unbalanced, which would show up mostly in the radial direction. And of course, you can just look at the belts and see the physical evidence. They'll be wearing out unevenly on the side.
So there you have it. We've identified all the suspects, we've cracked the codes, we know what the problem is, so now we finally get to move from diagnosis to correction. It's time to get things straight, literally.
And thankfully, modern tech makes this whole process incredibly accurate. Step 1 is to measure the misalignment with precision tools, like dial indicators or, these days, super accurate laser alignment systems. Step 2, the system does the math for you and calculates the exact fix needed, right down to the thousandth of an inch. And step 3 is making the correction, usually by adding or removing these thin metal plates called shims under the machine's feet until everything is perfectly lined up. So why does all this detective work matter so much? Well, get this. Over 90%, 90 of all problems with rotating machinery come down to just 4 things: unbalance, misalignment, looseness, or bad bearings. So if you can master how to diagnose misalignment, you are well on your way to solving the vast majority of machine failures before they even happen. So here's the big takeaway. We've seen how a tiny, almost invisible physical mistake can create these massive, destructive forces inside a machine. And that leaves us with one final thought. If that's true for machines, where might small misalignments in our data, in our team's goals, or just in our communication be creating hidden friction and all sorts of problems in our own work? Definitely something to think about. Thanks for watching.